In this lab, we will continue with the time series data analysis. In step 1, we loaded the time series data for COVID cases. We loaded confirmed cases, we loaded death cases and recovered cases from the website. And the files we loaded were with extension CSV. Then in step 2, we plotted 3 time series of confirmed death and recovered cases in mainland New Zealand. We excluded the Cook Islands and the New Year. In the graphs plotted, we found that the recovered cases, it stopped being recorded sometime in July 2021. And the death and the recovered cases increased as the time went by. Then in step 3, we had a snapshot in time, proportion of confirmed, recovered and death cases in New Zealand. We plotted that pie charts to show sometime before 2021, and we plotted the data for 2021. We plotted the data for 2020 and 2021. So the pie chart showed that 47.4% recovered and 51.9% were confirmed cases and 0.7% were death cases in 2020. In 2021, the confirmed cases were 99.8% and the recovered and the death cases were 0.1%. Then we plotted the Squarify plot, and to show the to compare the number of COVID cases in 2020 and 2021. We also plotted the bar charts to show the difference in the COVID cases in 2020 and 2021. So we can see that in 2021, the recovered cases were stopped being recorded. The confirmed cases were always the same proportion, and the death cases decreased. Then in step 4, we will perform autoregressive integrated moving average prediction on the confirmed New Zealand data to predict the number of cases in New Zealand. Let's first use the autoregressive integrated moving average function in statsmodels.tsa.arima.model to make autoregressive integrated moving average of 1, 1, 1. So autoregressive integrated moving average takes in 3 parameters, P, Q, and D. So we want to make autoregressive integrated moving average model for P equal Q equal D equal 1. From statsmodels.tsa.arima.model, import ARIMA. Hence, make sure that our confirmed New Zealand data is actually numeric and not object. Test this with data types. So confirmed New Zealand, The confirmed New Zealand data frame, let's run that, looks like this. And the data is from the fourth row index onwards. So let's select from 4 and onwards. And we can see that the numeric values starts from 22/1/2020 and ends on 9/3/2023. And we can see the data has been taken daily. Now, pandas.to_numeric of confirmed _ New Zealand of fourth row onwards, we will so this changes this data, which is of data type object, to numeric. So the data type is numeric, the data type is object, and we want to change it to numeric. And the way to change is using pandas.to_numeric of confirmed New Zealand of row 4 onwards. And we can see the data type is changed to int64. And int64 is numeric. Let confirm New Zealand num equal pandas.to_numeric of confirmed New Zealand of 4 and onwards. Errors equal coas. So errors equal coas means if there is a value that cannot be transformed to numeric, then just put not applicable. Nan, put nan. Confirm New Zealand, print confirm New Zealand num, and it prints this. You can see the data type is int64. Now let's check if there is any data rows which is NA. So confirm New Zealand num subset confirm New Zealand num dot is NA open and close bracket, and there is no rows. That is NA. Confirm New Zealand num dot index is all the data days. Make sure index is a date time index. Confirm New Zealand num dot index, let it be equal to pandas dot date time index of confirmed New Zealand num dot index. So we are changing the index to date time index, and printing confirmed New Zealand num dot index gives us this. So when we printed confirm New Zealand num dot index before passing this command, it printed and the data type was object. Now after doing pandas dot datetime of index, datetime index of confirmed New Zealand num dot index, so changing the index values, which are the dates, to datetime index type, the data type is changed to datetime 64 square bracket ns, and the frequency equal none. But we know the frequency is daily because the data has been taken daily. So set frequency, we know it, here is set to D for daily. So let confirm New Zealand num dot index dot frac for frequency equal D, capital D. Printing confirm New Zealand num dot index gives us the values, but the frequency you can change. You can see that it is changed to capital D, and the data type is datetime 64 square bracket ns. Now from statsmodels.tsa.arima.model, import ARIMA. ARIMA is autoregressive integrated moving average. Fitting ARIMA model, let model equal ARIMA of confirmed New Zealand norm, comma, order equal 1 to 1. Model fit, let it equal to model.fit, open and close bracket, printing the model fit, it prints this. So we need to, in order for us to do something for this model with this model fit function, we need to put some input parameters. Okay, so what we can do? We can make predictions from this model fit model. Model fit dot forecast bracket steps equal 10. So steps equal 10 will be forecasting 10 new values. So what was the last date for the date time index? That was 9th of March 2023. Now, so the predictions will be done from 10th of March 2023 because we put the frequency equal daily. And it is in, it will print the 10, it will forecast 10 values. So 3, 6, 9, 10. The frequency is D, name is predicted mean, and data type is float 64. Float 64 because the data is in decimal. We already imported this library, so we don't have to import the ARIMA library again. Fitting ARIMA model, let model equal ARIMA of confirmed New Zealand norm, comma, order equal 1, 1, 1. So equal P equal Q equal D equal 1. Model fit equal model.fit open and close bracket. So that will form a function. Diagnostics, print model fit dot summary open and close bracket. So on running that, we get a user warning. Non-stationary starting autoregressive parameters found. Using zeros as starting parameters on not non-stationary starting autoregressive parameters. So we can see that the number of observations is 1143. Log likelihood is minus 11,063.823. IIC and BIC, they are quite large. Model is ARIMA of 1, 1, 1. And the sample is from 22 January 2020 to 9/3/2023. And there are coefficients. So we can see that from the coefficients, all the values are very highly significant because the p-value is very low. It's almost 0. And there is little bit of skewness as well. And there are other parameters over here. Onyx covariance matrix calculated using the outer product of gradients, which is a complex step. Covariance matrix is singular or near singular with condition number 3.1 exponent plus 32. Standard errors may be unstable. Making predictions. Let predictions equal model fit dot forecast steps equal 10. So we get the model fit forecast where for the ARIMA model P equal Q equal D equal 1. So now what we will do is, So this is a repetition of what I have just shown. Okay, now there will be a warning sign. So to avoid to ignore the warnings being printed, we import warnings and we pass the command warnings.simpleFilter of action equal ignore. Let predictions equal pandas.dataframe of open and close bracket. This will initialize empty data frame. For P in range 0 to 3, for Q in range 0 to 3, for D in range 0 to 3, let name equal F apostrophe sign bracket, and inside the curly braces we'll have P, comma, space, curly braces Q, comma, space, curly braces D, and close the brackets. So what it will do, I'll just show you what it will do. It will print all the values, all the combinations of P, Q, and D, but we will separate the values by comma and space, and they will be enclosed by the curved brackets. And fitting ARIMA model. So model equal ARIMA of confirmed New Zealand num, comma, order equal P, comma, Q, comma, D. And model fit equal model.fit open and close bracket. Now making predictions. So predictions, we initialize the empty data frame. So now predictions square bracket name. So name will be each of these name. So those will be column names. Equal model fit dot forecast steps equal 10. Printing predictions, we get predictions data frame here with the columns with the 10 values which are forecasted, and for each of the P, Q, and D values. So we can see the column names are marked with P, Q, and D. Plot predictions. PLT.plot of predictions, use the numeric index for x-axis. So I'll just show you. And PLT.show open and close bracket. And we can see that these values are printed, and we can see the values on the x-axis are not very clear, so they need to be managed, and we also need to label each of the graphs. So rotate the x-axis ticks for readability. PLT.x ticks of rotation equal 45. So this will rotate the x tick labels by 45 degree. And when we run that, we get the X labels which are clear now. So we can see that the dates, the forecast date runs from 10 March 2023 to 19 March 2003. And now we need to label the graph, each of the graphs. For I in range 0 to predictions.shape 1. So let's check predictions.test dot shape. predictions.shape 1 is 27. So there are 27 predictions.shape gives 10 rows, 10 prediction rows by 27 columns. So there are 27 columns, and predictions 1 dot shape 1 will give us that 27. So 10 is for 0 and 27 is in place of 1. So for I in range 0 to predictions dot shape 1, so 0 to 27, plt dot text of predictions dot index. So predictions dot index, let's see what predictions dot index gives us. Predictions dot index, so that gives all the values, all the index values. So predictions dot index of 0. So predictions dot index 0 gives us the date 10/3/2023. So plt dot text of predictions dot index 0 will place the text value in the where the x value is equal to 10/3/2023, 10th of March 2003, and predictions dot ilog 0I. So predictions dot ilog 0 square bracket 0 will give us these values, all these values. So predictions dot index location 0 will give us these values. Now what is the I? What is the, say I value is 1. Then I value so predictions dot index location 0 1 gives us 1375592. So predictions dot index location 0 gives us all these values for on 10th of March 2023, all for all the column values for 10th of March 2023. So predictions dot ilog 0 gives us all the values for on date 10th of March 2023. And predictions, let's check what predictions dot index location 0 and 2 gives us, and that should give us 0 1 2, which is 1.805717 times 10 to the power 6. So let's see if it gives that. Yes, it gives us that. So that is what it does. So the y value is predictions dot index location for the first date, which is 10th of March 2023, and the and I for that column, for that particular column, and the value will be predictions dot columns I. So predictions dot columns are the column names, and say predictions.columns, which we chose was 2. Let's run that, and that is giving us 002, which is this one. So upon testing, it works. So now if I run this command for plotting the graph, it should label the graphs. So we can see that the predicted values, many values are 2.25 exponent 6. They are stationary at 2.25 exponent 6, and 000. Yes, so we see that for 001 and 002, they are non-stationary. Non-stationary up to the for 001, it's non-stationary from 10th of March 2023 to 11th of March 2023. And for 002 is the autoregressive integrated moving average model is the predicted values are non-stationary from 10th of March 2023 to 12th of March 2023. You might see the warning, value warning. No frequency information was provided, so inferred frequency D will be used. Self._in INIT underscore dates of dates.comma frequency. The warning message suggests that the time series data you are working with does not have a frequency associated with it, and the autoregressive integrated moving average model is inferring a frequency of D daily. While this is often fine and the model can work without explicit, so we have already explained about this, how we change the frequency to daily. And now the bigger problem is user warning. Non-stationary starting autoregressive parameters found using zeros as starting parameters on non-stationary starting autoregressive parameters. The warning non-stationary starting autoregressive parameters found using zeros as starting parameters generally indicates that the initial estimated parameters for the autoregressive integrated moving average model were found to be non-stationary, and as a result zeros were used as the starting values for optimization. In the context of autoregressive integrated moving average modeling, stationary means that the statistical properties of the process generating the time series do not change over the time. This is important for autoregressive models because they assume that the time series is stationary or at least approximately so. Non-stationary means that the statistical properties do change over time. In general, non-stationary series can have trends or changing variances over time. Now use tests like augmented decay FOLA, IDF testing from statsmodels.tsa.stattools to check if your data is stationary. So let's do that. Confirm New Zealand num is all the values from 22 January 2020 to 9 March 2023, and the frequency is daily, and the data type is int64, and length is 1143. Now from stats models to tsa.stattools we import @FULA. Let result equal @FULA of confirmed New Zealand num, and the result is this. So from the result we get IDF statistics, that is @FULA statistics equals 0.3451996 and so on, and the p-value is 0.979 and so on. The p-value is larger than 0.05, which fails to indicate that the time series is stationary. So the time series is non-stationary.